Hey folks, for this screencast, I want to talk about the DART mission, the Double Asteroid Redirect Test mission. If you noticed, if you've been following, on September 26th, a satellite, here's a satellite here in this image, crashed into, I think it was Dimorphos, the minor planet moon of Didymos. And I've been seeing a lot of different videos about the fact that they analyzed the data and it said that the orbital period of the orbit changed from 11 hours and 55 minutes to 11 hours and 23 minutes. And that got me thinking that if you know the orbital period, you should be able to compute the orbit before and after. And I haven't seen many pictures of the orbit before and after. And so I teach this in my spacecraft design course, and I thought, hey, wouldn't it be cool if we could just plot the orbits before and after? So that's what I want to do now. So I'm going to just import the standard stuff. You know where this is going. I do all my so I know my YouTube channel has some MATLAB in it, but right now I've been doing a lot of stuff in Python. So Didymos is the planet that is so this is the one that is orbiting the sun. So this asteroid has an aphelion, and it's helion for Helios because it's orbiting the sun, and Helios is sun. So yeah, it has 2.2 AU astronomical units. So that's twice the distance of the distance from the sun to the Earth. And the perihelion is 1.01. So this must be why NASA, or I guess the European Space Agency, actually I don't actually know, this was a NASA project? Yeah, it was a NASA mission. So this is why NASA chose this asteroid, because the perihelion is so close to Earth. So anyway, so I don't want to plot the orbit of Didymos. I need to get the mass of the planet. That's really all that matters. So there's the mass. It says the system is 5.4, but the mass of Didymos is 5.2 times 10 to the 11th kilograms. So M Didymos is 5.2 e to the 11 kilograms. Do they have the mean radius? There's the equatorial, there's mean radius, 390. I'm going to go ahead and put big R of Didymos at, that's a small asteroid at 390.0. So this is going to be mass properties of, center body, I guess is what I'm going to call it. I'm going to have my constants up here. And the only constant that I think we need is the gravitational constant, which is 6.67 times 10 to the minus 11. And then we can get the mass of the orbiting body, which is Dimorphos. And so we'll put in the mass of Dimorphos, and we'll go over here to Dimorphos. And the mass of Dimorphos, according to this, assumed is 5 times 10 to the 9th. So 5e9. I'm going to go ahead and I don't need the radius of Dimorphos. I actually don't even think I need the mass of Dimorphos. You know what I do need is, do they tell you how far away? So they tell you that the eccentricity is less than or equal to 0.03, which may as well be circular. So I'm just going to assume that the orbit before the impact, it says here pre-impact, was circular. So I actually don't need the mass of the orbiting body. What I need is orbital elements of Dimorphos pre-impact. Okay? And so the semi-major axis is 1.19, and that's in kilometers, so that's 119,000. And then what I do need up here is I need to compute mu, which is g times, this is the parameter, times the mass of Didymos. Sorry, that's not the parameter, that's the gravitational constant, times the mass. And then I'm going to assume the eccentricity is 0. So I can actually compute the orbital period of pre-impact again. So I'm going to say this is all pre pre-impact. So I'll put that in comments there. In the orbital period pre-impact, and I have this book called Fundamentals of Astrodynamics. It's there's a preface. So it's by Roger R. Bate and Donald D. Mueller, and it was written in 1971, I think. It's a really awesome book. But anyway, so there's an equation here for the orbital period. So you take 2 times pi over the square root of mu. So I'm going to do 2 times np dot pi over the square root of mu. And I have mu up there. And I guess I'll put Didymos, and I'll put A pre and E pre. That's pre-impact. T pre, and then mu Didymos, and then multiply this by the semi-major axis raised to the 3/2 power. And then I'm going to print the orbital period pre-impact is T pre, and this is in seconds. So I'm going to hit F5 there. I'm going to throw this on the desktop, and I'm going to call this dart.py. And sometimes it has an issue. Tony has an issue loading. So it says, whoa, that's big. So let's convert this to minutes. Wait, it was 11 hours, right? So let's convert this to hours. So T pre / equals 60, that converts to minutes. And then T pre / equals 24.0 converts, another 60. Converts to hours. So I could have divided by 3,600, but I didn't want to. So something is wrong here. Let's see, because they're saying it is 11.921 hours. So 2 times pi over square root of mu. Mass of Didymos, 6.67 10 to the 11th. It's in kilograms. Semi-major axis of Dimorphos is 1.19 kilometers. 1.19 kilometers. You swoop it 3 times. 1, 2, 3. That's 1,190 meters. There we go. 12.16 hours. So that's not quite what they have. They have 11.921. So I'm a little off. Trying to think what could be wrong. So my gravitational constant, let's look that up. Gravitational constant is 6.743. So let's put that in, see if that changed it. And that made it a little bit smaller. And then I am assuming a perfectly circular orbit, and if their eccentricity is even a little off, so I'm just going to leave it. I got 12.16. They got 11.921, so that's about the same. Let's now see if we can compute the velocity of our orbit. So velocity of orbit. So in order to compute that, we need the angular momentum, because the angular momentum is equal to the radius of the orbit, or in this case, since it's circular, the semi-major axis times the velocity. So if I can figure out the orbit, if I can figure out the angular momentum, I can figure out the velocity. Now, h is also equal to the parameter squared over mu. I'm pretty sure that is an equation in the book. And so I believe I should. So h is square root of p mu. That's right. Okay, so that's not quite right. Here is square root of p times mu. And I believe the parameter is a times 1 minus e squared. So p pre, the parameter pre-impact, is the semi-major axis times 1 minus e pre squared. The parameter is just the semi-major axis, but I'm just going to leave it there. The angular momentum pre is the parameter pre times mu of Didymos. And then that means that the velocity pre is h divided by the semi-major axis, at which point I can print velocity pre-impact is equal to v pre and in meters per second. Square root's not defined because I need to use the NumPy toolbox, and I get h is not defined because it's h pre, and I get 0.170 and they got 0.174, so I'm within the ballpark. So I've computed the orbital period and I've computed the velocity. So now what I want to do is I want to compute post-impact. Now before I do post-impact, I also want to, down here, I want to plot everything. Okay, so since the pre-impact is circular, things are really, really easy. I can say x pre is just the semi-major axis times the cosine of the true anomaly. And I'm going to assume, well, I'm not going to assume, the true anomaly goes from 0 to 2 pi, and I'm going to do 1,000 data points. And then y pre is just a pre times np dot sine of the true anomaly. And again, this is circular, so the orbit's easy. And then I'm going to plot x pre and y pre. I'm going to label this pre-impact. And then I'm going to throw a grid. I don't need an x and a y label, and I'm just going to show that. And I should get a pretty simple orbit. So there is my orbit of Dimorphos before impact. Okay. So now post-impact gets a little bit difficult. And this is why I'm making this video in the first place. They don't tell you what the semi-major axis is. All they do is tell you what the orbital period is. So we kind of need to back some things out. So the orbital period post is 11 hours plus 23 over 60 seconds, 23 minutes. Is that right? That's 23 minutes converted to, yeah, sorry, that's 23 minutes converted to hours. So let me repeat that. That's 11 hours plus 23 minutes. And I do 23 over 60 to convert to hours. And if I print, I don't need to print that. I can then go back to this equation here, and I can solve for the semi-major axis post. So it looks like if I do t post times the square root of mu Didymos, and then divide that by 2 times pi, that's equal to a post to the 3/2. So if I then take this entire thing and raise this to the 2/3, I should get a post. Now let's print semi-major axis post and see what we get. So according to this, oh, and this is in hours, I need to convert this entire thing to seconds to get the units to check out. So the semi-major axis post is 1,138, and it was initially 1,190. So according to these calculations, it did get smaller. Now there's some margin for error here because of the way I'm computing everything, but I have a new semi-major axis, okay? Now, I'm assuming, if I plot this, that at some point in this circular orbit, and I know this isn't perfectly circular, but like say, just imagine this is circular, the DART satellite hit it. Now, if we assume an instantaneous change in delta V at the impact point, that impact point becomes the new perigee. Because I'm assuming what happened was, or sorry, the new apogee. Because I'm assuming the DART spacecraft hit the satellite. So Dimorphos is going this way, the satellite hits it, and that's like a retrograde burn, which caused the top side of the orbit to come in. So that impact point becomes the new apogee, and the perigee shrunk. So the semi-major axis, A, is equal to the apogee plus the perigee over 2. If I assume that the apogee post is equal to the semi-major axis pre, because I'm assuming that at that impact point, the orbit shrunk in, that becomes my new apogee. I can then solve, if I do A post, which I know, times 2, and then I subtract off the apogee post, I will get the perigee post. And what I can do is I can print, and sorry, I'm saying apogee, it should be apoapsis because I'm orbiting a asteroid. So apoaps equals RA post, and then periaps equals RP post. I should be able to see a change here. And so now my apoaps is 1,190. My periaps has shrunk to 1,087. My semi-major axis is the average of the two, which is 1,138. So then I can compute my new eccentricity, which is RA post minus RP post over 2 times the A post. And by the way, I know a lot of these equations by heart. They are all in this textbook. I've just done this so many times that I know these equations off the top of my head. Okay, so now I have the eccentricity, and I'm curious, what's the new eccentricity post-impact? Because remember in the Wikipedia post, it said that it was less than 0.03 before impact. Well, what is it after impact? Well, after impact, it went from 0 to 0.04. So I guess that's not that big of a change. But actually, here's the thing. You're talking about an asteroid that is the aphelion is 2 times the distance from the sun, and the perihelion is the same as Earth, roughly. And NASA scientists launched a satellite at it and collided with it, and according to my calculations, changed the eccentricity by 4%. Okay, maybe that's not a lot, but maybe if we put it into perspective, that is quite a lot. So we have the new eccentricity, which means we can compute the new parameter. So the new parameter is A post times 1 minus E post squared. I don't need to print the parameter because the parameter doesn't really do anything. But what it does do is it will allow me, we can compute the velocity. That'd be cool. So angular momentum is conserved, right? So H post is NP dot square root of P post, because the parameter is a constant, H is a constant, times mu of Didymos. So that computes the angular momentum. And so now I can compute the velocity at apoaps, which is just the angular momentum divided by the apoaps itself. And then the velocity at periaps is just the angular momentum divided by the periaps itself. And then I can print velocity, apo is VA post, and then velocity peri is VP post, right? And so if I print that, this is going to be really cool. Okay, so see, this is neat. So velocity pre-impact, oh dude, this is so cool. So the velocity pre-impact was 0.17. It was constant, right? Now, this is so neat. The satellite collided with Dimorphos at the new apoaps of the orbit. So it decreased the velocity by 0.004 meters per second, which caused the periaps to come in on the other side. Now, what that means is that the overall energy of the orbit decreased, but because angular momentum is conserved, once Dimorphos came around to the new periaps, it actually sped up to 0.18. Now that makes sense because the orbital period went down. Like, it's kind of weird to think about the fact that you crashed into a satellite and you basically removed energy from it, but it sped up. Because basically what you did is you caused Dimorphos to fall into Didymos's gravity well and caused kinetic energy or potential energy to convert to kinetic energy. And so it actually sped up, which is really, really freaking cool. Okay, so I think we almost have everything we need. We need the radius post-impact as a function of, I think I should do this in the plot everything spot. So this is going to be pre-impact, and then this is going to be post-impact. What we need to do is compute, so the radius for a circular orbit is constant. The radius for an elliptic orbit is not constant. It's actually equal to the parameter divided by 1 plus e times the cosine of the true anomaly. And again, for a circular orbit, right, the eccentricity is 0, so the radius is constant since the parameter is constant, and the parameter is equal to the semi-major axis, and so everything kind of just simplifies out. So that radius is going to change. So then I'm pretty sure I can just do the exact same equations, except change these to x post and y post. And then this is not a pre anymore, it's r post and r post. And again, because the radius is changing, this should all shake out. And then I should be able to plot x post and y post and do a post impact. And then I need a label now, or a legend, sorry. And I should be able to write that, and let's see how much it changed. That is badass, okay? NASA engineers built a satellite that, the point of impact is over here. That's the intersection point of the two orbits. So NASA engineers took a satellite, launched it into space, crashed it into a, how big is Dimorphos? Crashed it into a 170 meter rock and decreased the circular velocity speed by 4% basically, such that now, rather than it being this blue circular orbit, it is in this orange elliptic orbit now. Now that is super freaking cool. And that is exactly what I wanted to do to this video. That's the entire purpose of this video. I've been seeing a lot of videos out there where people are talking about like, oh yeah, they're still doing the math. They're still calculating like how much it changed. Like there it is. There is a visual representation of how much the orbit changed pre and post impact of the DART satellite. I'm really psyched that I got this to work. I hope you guys really enjoyed this video. Post in the comments if you enjoyed it, and if you have any suggestions for another video, let me know. I'll see y'all on the next one.